That's what I think I had the camera on, so it was like this one.
So that ended up being a simple one. This one, 3.500. Milliliters to gallons. Kiloliters. I think we have liters to gallons. I think what we have to do is get rid of the kiloliters, get to liters, and then go liters just to gallons. So we've got to find those relationships. Do you know what this one is, kiloliters to liters?
10 to 3 liters.
I'm going to do it like this. 1 kiloliter is 1,000 liters. And the gallons to liters should be here somewhere. Volume. 1 gallon is 3.7854. Or did I do that backwards? I'm looking right here.
No, that's right.
No, that's right.
Volume of the last one.
So this is saying 1 gallon is 3.7854 liters. Kiloliters cancel, liters cancel. We're left in gallons, so that's right. English and metric. So this is exact, and has significant figures. This is metric to metric. Both of these are exact, and then this one is always exact. So my significant figures are all coming from here and here. I think there might be a problem. Let's see. I thought I went through all of these. Calculator. Okay, 3.500 times 1,000 divided by 3.7854. Anybody else do this with me? Should be 24.6. Oh, yeah, that's right. Question 2, when you can harder conversions, it's that. Do you see why that's the right answer? So 4 significant figures, the 0 does not round to 6, so we ended up.
Did you multiply this together, or do you divide?
In my calculator, I went this times this divided by this.
Oh, I forgot.
I ignored the ones. You forgot the 1,000? That's fine. All right. question 5, the harder conversions. Question 5. The roll of wire is 20 millimeters. What is its length in miles? All right, and I'll start by going millimeters. I'm probably going to go from millimeters to meters and then meters to miles. I'm guessing that's what I have. Miles to meters. 1,000 millimeters in 1 meter. And then my miles to meters are I've got miles to kilometers. So you want it's just meters to miles? No? Okay, so that's another conversion. So 1 mile is 1.6093 kilometers. 1.6093. That'll do it.
See all these extra conversions I have to do? That's what's in this file.
So there'll be 1 or 2 of these harder ones. Test.
Equal calculated out. Got a power of 10 to deal with too.
I'm going to separate it into numerical values, powers of 10, and units, like I've done before. Let me go up above here though. Meters, kilometers, miles. One, 1,000. No more powers of 10. Now we have millimeters. So we double check. So cancel. Yep, miles, which is what we expected. 10 to the 5 is already on top and by itself, so I'm just going to go times 10 to the 5. So the rest is just a calculator. How many significant figures do we need? 3. 1.2.
divided by 1,000, divided by 1,000, divided by 1.603.
Calculator says.
And I have to fix that one. Number 5. We have that, and we have times 10 to the 5. So we ought to go ahead and apply that. One, 2, 3, 4, 5, so 0.198844217. It's 3 significant figures, is that right?
Do you not use the 1.6793? Is that exact? So is that why you don't use it?
We did, but,
Oh, it's the lowest, yeah.
exactly, it's the
Okay, yeah.
lowest.
I have to fix my answer key though.
So it's 3 significant figures, it's the 1, 9, and 8. 8 rounds to 9, so it's 0.199.
For the test, will maybe they're going to come later?
Yeah, in fact, those that were out on the counter earlier last week, using specifically those.
Okay. Okay, that many meters to 1 millimeter. You're looking at. I'm gonna use. Okay. What you're looking at tells you 1 millimeter. Right?
Oh, so you can just like flip it.
Well, look at this. 100 over 100 is 1. So that's not going to change the value of this at all. So after I do that bit of math, it's still a conversion factor for meters to millimeter. If I do that, I get. I've done something wrong. Is that what it said next to millimeters?
Yes.
You do this. 2, 3 times 100. Oh. So that turns the bottom into 1 and the top into
That was the
1,000.
bottom. I thought that was the bottom. Or, wait. Oh, okay.
So it still,
Yes,
still
yes,
equals.
yes. I see.
Can you explain to us what exactly you put into the calculator for this problem?
Yeah. Good
And
question.
what you were doing up at the top of the board?
Say again?
And what you're doing up at the top of the board?
This is just all of this rearranged,
Okay.
categorized. I get all the numerical values together, and I get all the powers of 10 together, and I get all the units together. Powers of 10, units, and all those numerical values.
Okay.
That just makes it easier to see for me, because this you're not going to solve with your calculator, you're going to solve by canceling. This you solve by following rules of exponents, which you still pretty much do by hand. And then this is what you put in your calculator. 3 different strategies for 3 different types of data to deal with. And just to help your eyes, because to me that looks a lot neater than this spread out down here. And then what I did in my calculator is, when I have it all like this, I know I can ignore the ones. So I just put in my calculator 3.20 divided by 1,000, divided by 1,000, divided by 1.6093. Does that make sense?
Yes, sir.
Was I gonna do another one? Conversions, harder, preview. Let's do the fluid ounces. Do you have a guess what the right answer is before we do the calculation for number 9? It has to do with significant figures. I probably shouldn't have written this question that way. What's the question number? 9. So this is 9 in the harder conversions. .065 kiloliters. We need it in fluid ounces. Put it in fluid ounces. I'm sure we're going to have to go from kiloliters to at least liters. Let's see what we've got for conversion factors. Volume, got gallon to liter. Quarts, we've got fluid ounces in quarts here. So we're going to need quarts. 1 liter to 1.0567 quarts. Quarts. Already forgot it. There it is. 1 liter is 1.0567 quarts. 1 liter, this is 1,000 liters is 1 kiloliter. Now I can go from quarts to fluid ounces. So in here, 1 quart is 32 fluid ounces.
What is a GT? What is a GT?
Oh, that is ugly handwriting. That's my cube. That's supposed to be quart. My cubes look exactly like a G. All right, I looked this up. It's 32 fluid ounces to 1 quart. These are both exact because it's English/standard. Quarts to liters. This is metric to English. One of them is exact, the other one is got significant figures to deal with. Metric to metric, both of these are exact, and this is exact. So all our significant figures are coming from here, here. Everything else we can ignore for significant figures. Everything else is exact. You follow? You want me to split this one out like I did before? Okay. All ones on the bottom. There's no powers of 10. Kiloliters, ounces, quarts, ounces, kiloliters, liters, so quarts cancel, liters cancel, kiloliters cancel, we ended in fluid ounces, that's what we wanted. And then only one of those answers on there had two significant figures. Probably ought to fix that up a little bit. So I'm going to go 0.065 times 1,000 times 1.0567 times 32. Our calculator says, so how many significant figures? We're looking here and we're looking here. Two significant figures. Those two, the 9 rounds the 1 up, and then those become zeros and we don't put a decimal here. Definitely be practicing these.
So how do you determine like what is exact and what's not exact? Because like I understand why the first number isn't exact, because like if they really give that to you, so you can't be exact. But then I'm just curious as to why the 0.0567 equals to 1 liter is exact. Is it because you're going from English to metric?
Yeah, the odds that they would be exact out to an infinite number of digits is just they would come up with a completely different way.
When it's English to English, it's exact, metric to metric, it's exact, English to metric, it's not exact.
Exactly.
Got it.
English to English, those are all just straight up definitions. People made up, so they're exact. Metric to metric was designed to be exact, just the power of 10. But when you got to go from one system of measurement to a completely different system of measurement, they're not going to match up 1-to-1 anywhere.
I'm so sorry, but I am very scared of spiders and that's even.
It's the second spider we've seen down here. That's why I don't like killing them. They're so gross once you kill them. All right. Thank you. Handling the spider. I was hoping once it got cold down here. All right, let's do some on density. Yes.
How come we just made it 2200 and then put it in the scientific notation?
If you were at put into scientific notation.
Yeah, like before, just like when it was 2,197 point whatever.
Okay, what was it?
It was 2,197.963.
Yeah, and you want me to put that in scientific notation?
I was asking, would you put it in the scientific notation or is it okay to just?
I would only put it in scientific notation if I were asked to.
Okay.
But if you were asked to do it, first you're gonna set your significant figures. So you would have gone 2, and the 9 rounds that, and you got 2,200 with no decimal. And then from there, the very last step is putting into that standard scientific notation. That only comes up at the very end.
So you would still do that step anyway?
Yeah, that step. That was just identifying significant figures.
Thank you.
And in case you wanted. That's that number put in scientific notation, and it's worth noting that the zeros weren't significant, so they're not there in scientific notation. Density problems. These should be simple. These density problems are very simple. There's only 3 ways you can be asked a simple problem on density. One is you're given the mass and the volume and asked to find density, like this one. Do you know what you do here?
It's, like counting
It's grams over milliliters. So you just do this. Oh, I guess that's 1 significant figure. I need to change that. That should be 2. Nobody does calculations in 1 significant figure. So I get 1.5, and you're just going to go grams per milliliter per units. Truthfully, this should have a period there. I don't remember if it did or not in here. No, it needs that. Let's- A sample of something is there's its density, its volume, you know what to do here? What are you going to do with this first?
You gotta do it in the fraction of grams at the top.
You want to write it like this. Grams to 1 milliliter.
And is that 1 milliliter exact?
Yep.
Okay.
This one, we're just going to do right on this side, 8.0 milliliters. That will make the milliliters cancel, and we will be left in grams. How many significant figures do we want? 2. That's what my calculator says. The 6 rounds the 9 up. There's my 2 significant figures. The 6 will round the 9 up. So we end up at 90. These should be easy, these density ones. So I showed you mass and volume by density. I showed you density and volume by mass. The only other way you get one of these simple problems is, let's see. So given density and mass, find out how many moles. And in this case, this we're going to flip over. So we have grams on the bottom now. Divided by 11.2.
Would it be 5?
This is still 3.
I thought that was exact.
That's exact.
Oh, okay, that's not, got it, okay.
Calculator says 7, 4. Why am I writing all these? 7, 1, 4, 2. But we're only keeping 3. So. That's the answer. 9.07 milliliters. So there's a bunch of those to practice. What have we not done? Could you do these? Convert 150 pounds to kilograms, and then you're given the relationship pounds to kilograms. And then quarts to liters, and you're given the relationship.
This
Could you?
is back to the imperial measure.
Hmm?
This is, we're going back to the imperial measure.
Yeah. I don't think I went into these. Did I do these?
Is the 150 exact or no?
It's two significant figures.
Okay, all right.
And the other one. Times 0.4536. 68.04, but we're keeping two significant figures, so it just ends up with 68. And .1892 liters. Three significant figures, three there, so it's the one. The camera on. All right, so two quick examples. Convert 150 pounds to kilograms. You have this relationship. There it is, done. Convert 2 quarts to liters. There's the relationship, quarts to liters. And it's the final answer. That's the final answer. I didn't have that on camera. All right, I know what else we can do. Haven't done yet. There is a section in this book on temperature conversions, but notice that everything we've been doing, when I say conversions, only had multiplication and division involved. And that's true nearly all the calculations we do. There's very little addition and subtraction. But when it comes to temperature conversions, we do use addition subtraction. So we're going to Kelvin, 3C plus 273.15. So converting between Celsius and Kelvin, and then converting between Celsius and Fahrenheit. And I'll give you those formulas, so that's why I waited to do these because they're really easy. Had any? No, I don't have any in the database. I'll have to make some. Well, let's see. So there's your degree C. We're trying to come up with Fahrenheit. In this case, it's 1.8 times 36.2 plus 32. We rarely have temperatures measured to more than 2 significant figures. So that's why these factors in here they don't even bother to go beyond. All right, 1.8 times 36.2. So I have, these are my significant figures. So I'm going to include those in the calculation, but this is to remind me that this is 2 significant figures. And plus 32. It's 2 significant figures, so 97. Put that on the wrong side. So that's going from Celsius to Fahrenheit. Fahrenheit to Celsius. Let's see where we are at. So let's do it again. Now, we're trying to get Celsius from Fahrenheit. I've had this habit for years. Put that on the wrong side. So you just complete that math. If you're trying to get to Kelvin from Fahrenheit, the best thing to do is go through 2 steps. Turn it into Celsius and then just do the simplification here.
And then you count 32 and 1.8 as significant figures, so that's why you only need 2 in this case.
Yeah.
Okay.
They do that because rarely do we measure temperatures to more than 2 significant
Okay.
figures. I know we don't measure it any higher than that in here. Be careful here. Oh, 4.2, so I didn't have to do that. All right, divided by 1.2. I got 2. And I guess I'll do one of these. Celsius to Kelvin. Do you know what the Kelvin scale is?
Zero is like absolute zero is like coldest degree, right?
That goes to absolute 0. So we haven't talked chemistry yet, but it's 0 degrees Fahrenheit or 0 degrees Celsius. There is still motion, there's movement, there's still energy there. Those were just kind of arbitrary scales. Celsius uses, the freezing temperature of water is 0, and then the boiling temperature of water is 100, and then just made 100 tick marks in between those two. But at 0 degrees Celsius, there's still molecular movement. So if you have a gas, you're in the gas state, the atoms or molecules are moving around really fast. When it condenses into a liquid, enough energy has been removed from all the movement that they'll kind of stick to each other. They don't stick hard, but they kind of stick like if you had a bunch of magnets in a box and you were shaking it, they're still kind of sticking to each other, but they're still like swimming around each other. And then when it goes from a liquid to a solid, they do actually freeze in place, but they still vibrate. So even this solid right here is vibrating at a certain frequency. Everything in this solid board here is still vibrating. But if you all the way down at 0 degrees Kelvin, everything is frozen completely. I think there is a tiny amount of quantum motion. We call it a zero energy. You heard of that, Ellie? A little bit, yeah. But that's what absolute zero means. All but the tiniest of tiniest little movements are gone, and now all that's left is this sort of quantum effect type of movement. But so that's what the Kelvin scale is. What do I want to do here? Let's do 75 degrees. Do it again. And then Kelvin equals and that's all there is to it. So 75 degrees in Kelvin is 273.15 plus 75. Except I have nothing after the decimal here and 2 here, so I have to have nothing after the decimal here. The 1 will not round to 8, so the answer here is 348. Okay. And we just say Kelvin, we don't say degrees Kelvin.
Why would it not be 350 since the Celsius?
Oh, no, because it's the addition subtraction. You only pay attention to what's after the decimal.
Okay.
The rest of it doesn't.